Good morning, Bryn. Let's take a look at number 8 first. The question is how many 3-digit odd numbers greater than 600 can be formed using the digits given, and you're not allowed to repeat the digits. So what you're doing is you're arranging the digits. You can't use them over and over again. This is a tricky one because if it's an odd number, that means it has to end in an odd digit. And the odd digits are 3, 5, and 7. But there's a bit of a problem because if the number has to be greater than 600, then that means it can start with a 6. Any of these arrangements that starts with a 6 will be greater than 600. Or it can start with a 7. If it starts with a 7, then it's going to be in the 700s, and 700s are bigger than 600. But here's where the problem comes in. If it starts with a 7, then that affects the number of different odd digits that you can put at the end. So for example, if we have a 3-digit number that's in the 700s, then the number of odd digits that we can put in the third place to make the number odd is only 2, because we're using a 7 in the first place, which would only leave a 3 or a 5 in the final place. On the other hand, if you had a 3-digit number that was in the 600s, that means the first digit has to be a 6, the last digit has to be odd, but if the first digit is a 6, then for the choice of the last digit, which must be odd, you can choose a 3, a 5, or a 7. So the number of different choices you have for the final odd digit depends on whether the number starts with a 6 or the number starts with a 7. And because of that, we are going to have to find the number of 3-digit numbers that are odd that start with a 6 and the number of 3-digit numbers that are odd that start with a 7. And again, if it starts with a 6, the final digit must be a 3, a 5, or a 7. On the other hand, if it starts with a 7, the final digit must be a 3 or a 5. So we're going to use the fundamental counting principle here. We're going to add these two results together because it can either start with a 6 or a 7. So how many 6s are there in our list? Well, there's only one. Multiplied by 3, we have to take care of the restrictions first. So we looked at the first blank, it must be a 6. We're looking at the third blank, which must be a 3, a 5, or a 7, and that means there's 3 choices. Now, if you count up the digits we had a 2, a 3, a 4, a 5, a 6, and a 7. And that's 1, 2, 3, 4, 5, 6 different digits that we started off with. At this point, we've used 2 of them. You've used the 6, and you've used 1 of the 3, 5, or 7. So you've only used 2 of the 6. That means you have 4 left. So the number of 3-digit numbers greater than 600 that are odd in this example is 12. 1 times 4 times 3. If the 3-digit number starts with a 7, then there's only one choice for the first digit. It must be a 7. There are now only 2 choices for the third digit because we've used the 7 in the first place, and that leaves only 2 odd numbers remaining that we can pick from, a 3 or a 5. So there are 2 choices for the third place. And then it's a 4 in the middle again. We're not saying we're choosing the digit 4. We're saying at this point in time, there are 4 digits left that you can select from. So the number of 3-digit odd numbers greater than 700 is 8. And again, the word or means add together. So if we take 12 plus 8, you get 20. So the correct answer must be A. Number 26 is a question which you can easily overthink. You do need to have some knowledge of the structure of a deck of cards. In a standard deck of playing cards, half of the cards are red and half of the cards are black. There are 26 red cards and there are 26 black cards. And the question is, if you're going to be dealt 5 cards randomly out of the deck of cards, how many possible hands will have cards that are all the same color? Well, they could be all red or all black. And here's the place where you can easily overthink it. If you want to find out how many different 5-card hands are all red, all you have to do is say there are 26 red cards and I need to choose 5. So 26 choose 5 is going to be the number of different 5-card hands that are all red, plus, because it's or, to get a 5-card hand that's all black cards, you're going to take the 26 black cards and select 5 of them. I don't know what these numbers work out to, but when you calculate 26 choose 5 plus 26 choose 5, you should get the answer. All right, question 30 says we have 5 different types of fruit and 6 different types of vegetables, and we're going to be making a snack tray. The conditions are that you need 2 fruits and 3 vegetables, but you have to have either blueberries or carrots. And if you have blueberries, you cannot have carrots, and if you have carrots, you cannot have blueberries. That's the condition, is you cannot have them both. Because of that, I'm going to take the items that are fruits, and I'm going to break them down into 1 blueberry and how many fruits did we have? 5, 4 other fruits. And I'm going to take the veggies, and because of that condition of you have to either have carrots or blueberries but not both, I'm going to break the 6 vegetables down into 1 that's carrots and 5 that are other veggies. So let's look at this logically now. You need a fruit tray that contains blueberries but not carrots. Or you can have a tray that contains carrots but not blueberries. So when we build our tray that contains blueberries, I'm looking at my category of fruits here. I need a blueberry. What else do I need? Well, I believe that we had to have a total of 2 fruits on each tray. We need 2 fruits and 3 vegetables. So if I have blueberries, that means I need 1 other. So I need 1 more other. Well, let's fill in these numbers. There's 1 blueberry times, well, I'm going to put 4 choose 1. We could just put the number 4, but I'm going to use choose or combination notation. Now, we also need on that tray, so this was 1 other fruit. We also need on that tray 3 vegetables. So I'm going to go back up and look at the highlighted part. It says I need 3 vegetables. But here comes the tricky part. I need 3 vegetables that do not include carrots. So I need 3 non-carrot fruits. And when I look at my categories for fruits, I have 5 vegetables that are not carrots. So I need to multiply by 5, and I'm going to choose 3 of them. So if you figure out what 4 choose 1 times 5 choose 3 is, what you're going to get is how many trays contain blueberries but not carrots. Then we have or. Well, what do we need here? We need carrots and, just a second here, how many vegetables do we need? We need 3 vegetables. So carrots is 1 vegetable. We need 2 other vegetables. So when we look up top here, we have 5 other vegetables that we can choose from. This will be 5, choose 2, because we need 2 others. And of course, there's only 1 carrot. But this tray also needs fruit. And when we look at the top, I've highlighted that you need 2 fruits, but since this tray that we're working on has carrots, the condition in the question was that it cannot have blueberries. So we need 2 non-blueberry fruits. So when I look at how many fruits are not blueberries, there are 4, and then I need to choose 2. So if you take 1 times 5 choose 2 times 4 choose 2, that's how many trays contain carrots but not blueberries. And we have to calculate this and this and add them together. So let's see what we get. It's a very confusing question. I don't need to write 1. I'm just going to go 4 choose 1. Well, that's 4, but I'll actually enter it 4 choose 1. Then I'm going to multiply by 5 choose 3. So the number of trays that contain blueberries but not carrots is 40. Let's take a look now at the number of trays that contain carrots but not blueberries. That's 1 times 5 choose 2 for the 2 non-carrots, or the 2 other vegetables that are not carrots. And we need to multiply by the 2 fruits that are not blueberries, so that's 4 choose 2. And you get 60. So there are 40 trays that have blueberries but not carrots. There are 60 trays that have carrots but not blueberries. So if we look at our choices, 40 plus 60 is 100. I'm pretty sure the answer is 100. And the final question here is a really strange question. It has to do with the binomial theorem. What you need to remember is that when you have a binomial raised to a exponent, I'm just going to say n, this will have n plus 1 terms. Always. So when you have x plus y to the 12, you're going to get 13 terms. Now, if you think backwards here, if there are 23 terms, then that must mean that the exponent is 22, because you always get 1 more term than the exponent. And if we want to find the value of k, what we're going to do is say that k can be found by taking the exponent, 3k minus 5, and setting it equal to 22, because we know the exponent has to be 22. I'll repeat that. The exponent is always 1 less than how many terms you get. So if we get 23 terms, then the exponent must be 22. Since the exponent is 3k minus 5, 3k minus 5 must equal 22. And it becomes a matter now of just solving that for k. Adding 5 to both sides and getting 3k equals 27, dividing both sides by 3 and getting k equals 9. So the correct answer would be B. I hope that made sense. Same thing as I told you yesterday with some of these. If you need further clarification with any of these questions, fire off another email to me. And I hope you have a great rest of the day, and we'll talk to you later.